Starting a little bit late. That's okay. So you got your test back. I'll post the grades on Moodle, but I held off to reward those who come so that they can see their test grades right away. Okay. Our last chapter. Can you believe it? Yes, you can. You're supposed to say no. I can't believe it. It's so exciting. This is our last chapter. What's nice is this will be the only chapter that you will not have seen on a test, right? And so you'll see it for the first time on the final exam. But on the plus side, it's going to feel very similar to the chapter that we just finished, chapter 7. So that's nice. We're just kind of extending it into probability. Any questions about the test, though, before I jump into probability? No? No questions? Okay. So, first thing we need to talk about in terms of probability are sample spaces. And if you've taken a stats course before, then you'll be glad to know that all of the probability that we're covering, pretty much all of it, you'll have seen in the past. So that's really nice. I love it. Or I used to love it when I was taking courses and I was learning kind of the same stuff in multiple courses. It's like, oh yeah, got that. Good. Okay, so let's talk about what is a sample space. Okay, so a sample space, I'll just do it here, is a list or a set of possible outcomes. Okay. So when you flip a coin, for example, the possible outcomes would be heads or tails, right? We've worked with flipping a coin before. Okay. Rolling a die, right? You get one, let's assume it's a 6-sided die, 1, 2, 3, 4, 5, 6, right? Drawing a card, there are 52 cards in a deck and there's different kinds, right? And so, or surveying people, okay, those are called experiments. And so a sample space of an experiment is the set of all possible outcomes. Now I will add that in one experiment, only one of those things will happen. Okay? And so even though there's a list of possible things that could happen, only one will happen. Okay? Only one will happen. Say each time, right? So if you flip a coin, for example, right, then you know you're going to get heads or tails and you can't get both. But those are the only two options. Usually what we do is we denote it by a capital S. And so the sample space is denoted by a capital S. Which means that if a die is rolled and we want to write the sample space, right, then S is going to be the set of 1, 2, 3, 4, 5, 6. What if I asked you a follow-up question, right? What's the probability of rolling a 2, right? The probability of rolling a 2 is going to be 1 in 6, right? But what does that stem from? Kind of working backwards here, right? That stems from there being 6 possible outcomes, right? And so one of those outcomes has a probability of 1 in 6. Okay? And so here we have 6 possible outcomes. each outcome has probability 1 in 6. Huh? Flip a coin, right? If you think about flipping a coin and I ask you, hey, what's the probability of flipping tails? You would probably say 50% or 0.5, right? And that's because there are two possible outcomes and tails is only one out of those two outcomes. And so that's why we need the sample space. This idea of the sample space is because it's going to be the total in the denominator for our probabilities. Now, I will bring in, where's our formula sheet? We're on to the last page of your formula sheet. I set it up not to brag or anything, but kind of nicely, I thought, because it was test 1 on page 1, test 2 on page 2, and then final exam, new stuff for final exam on page 3. Now today, we're going to do a lot today. Holy cannoli. Makes you wonder if we need to show up. We do. Well, I do. I don't know if you do. For the rest of the days. So I want to bring in what's on our formula sheet because if A is an outcome of a sample space S, right? And so just to show you this notation here, that's why we had to introduce what the sample space is, right? And that we denote it by a capital S. And then I'll leave the rest for just a little bit longer. We'll do some practice with the sample space first. I'm going to change this a little bit, right? The sample space for the gender combinations. And I will clarify that we're going to assume male, female are the only two, only because it makes our tree easier. Right? And so we'll start there. So a family has 3 children. And so whenever you have consecutive events, right? Some first event, so first child, second child, third child, right? That's a perfect use of a tree diagram, right? And so you have your first child here. So child number 1 is either male or female. And whenever we want to list the possible outcomes, right, then a tree diagram is usually the way to go, right? And so we've got the male, female, and then we had child number 2, and it doesn't matter what the first gender was, male, female. You have the same options for the second child as well. And of course, the third child, right, coming off of each of these branches. So 1, 2, I'm gonna need to do it a little bit smaller to keep it on the page. That's okay. So child number 1 again. They're all number 1, number 2, number 3. There, fixed it. Male, female, male, female, male, female, male, female. So now, at the end of each branch, right, we can write what all the possible combinations, gender combinations are, right, which would be our sample space. Right? And so I have male, 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 which is different, of course, from male, male, female, male, female, male, male, female, 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 male, male. And we're used to doing this, right? And so that's why I'm going relatively quick. Female, male, female, 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 male, female, female, female. So now, the only new thing that we're introducing really, right? Because if I asked you, hey, a family has 3 children, what are the possible combinations of genders, right? And so then you would already know how to do this, right? And so the only new thing that we're introducing here is that now the sample space is all these outcomes. Huh? And I mean, technically they should be separated by commas, but I usually don't. I usually don't even say that it's a sample space, but technically it is. So now we can use this tree if we wanted to, and we could find, okay, well, what's the probability of 1 female? Right? There's lots of different ways that you could have 1 female, right? Here's an option. So there's the first option. Here's a second option. This is 2, so it doesn't count. Here's a third option. This is 2, 2, and 3. So I have 3 out of 1, 2, 3, 4, 5, 6, 7, 8, right? And so the probability of having 1 female is 3 out of 8, right? I'm getting ahead of myself, but this is kind of my wheelhouse, so I'm allowed to. We were just asked to find the sample space, which we did. Nice. Any questions? This one, I'm not going to make us write it out because that's crazy and just very tedious. And so I've included this kind of summary of 2 dice being rolled. So 2 dice are rolled and we want to write the sample space. This is only to keep track of the first die versus the second die, but let's assume that one of the dice is red and the other is green. And so here we have our first die, which is red, and then we have our green die here. But of course, the possible outcomes for the red die are 1, 2, 3, 4, 5, 6. And for the green die, 1, 2, 3, 4, 5, 6. How we list these combinations, right, is first the row, then the column. So 1, 1, 1, 2, 1, 3, 1, 4, right? And so in general, row, column, oops. All right, listed as row, column. And here we have all the possible combinations. Right? Of course, it matters if the first die is a 2, right? As opposed to the second die being the 2. Right? Sometimes you both roll 2s, right? But the first die rolling 2 is this row here. And then I should say the red die rolling a 2 is this row, right? Whereas the green die rolling a 2 would be this column, right? And so it depends on which one. And so this is the sample space, this whole thing. Now, I'm not even going to bother writing that out as a set, right? But those are all the possible outcomes. Which is all we were asked to do. We are going to come back to this. A really common example that we use is we use the sum of 2 dice. Yeah, dice. I have to check because singular is a die, and a student told me once that you can only die once, and so that's how they remembered it. And so it's one die, two dice. But I always have to use that in my head. And now I said it out loud. Oops. Um, so we use the sum of two dice quite often, but I've got that Martha Stewarted already, which is like pre-baked in the oven, ready to go. Now, probability. The definition of probability is going to be really, really important. Okay? And it is on your formula sheet. So we'll read this definition first, and then we'll go back to your formula sheet and just kind of confirm that it's all there. But for a sample space S and an outcome A of S, and so any one of these things or multiple things could be part of A of S. The following two properties are satisfied, not only satisfied, but they have to be true. And so if A is an outcome of a sample space, which it will be, then the probability of A, which we denote by P of A, and I'll do this down here. You read this, read P of A. But technically it means the probability of A. Or the probability of A. Whatever you have in the brackets, you read as of, right? And so the thing outside and then of A, whatever's on the inside. Right? And so you might be familiar with something like f of x, right? You read it the same way, right? F of x is function notation. Whatever you want. Now, the probabilities have to be between 0 and 1. It's impressive. So probabilities have to be between 0 and 1. Okay? And so I'm going to highlight that as much as I possibly can. They're allowed to be 0. If I say, hey, the probability of that is 0, then you know that it will never happen, right? And if I tell you, hey, the probability of that is 1 or 100%, usually we convert to percentages for when we're talking about probabilities, right? And so if I tell you, oh, that's the probability of that is 100%, then you know it's definitely going to happen, right? And so, and it's allowed to be any value between 0 and 1. So here, as a fact, probabilities must be between 0 and 1. We often convert them to percentages, right? But percentages from probabilities between 0 and 1 have to be between 0 and 100. And so we often convert to percentages. So the percentages have to be between 0 and 100%. Just multiplying 0 and 1 by 100 on either end. It doesn't come up so much in this class, but as a fun fact, How about an LFF? A little fun fact. Do this. A proportion is a probability, which, and only because I'm super picky, is almost a percentage, right? You multiply by 100, but that's why I have the squiggly equals, right? And so is a percentage, which means that all these three P's, we can use them interchangeably, right? I might say, hey, what proportion is this? That is a probability, right? And what percentage, of course, is also a version of a probability. And I shouldn't have, oh, it kind of works out actually. It's down here. So probabilities have to be between 0 and 1. Huh? And so if I see probabilities that are not between 0 and 1, then it makes me really sad and then a little bit mad. So don't do that. It's not true. Can't be. No. In the end, I just take a mark off. The sum of the probabilities of all the outcomes in the sample space has to equal 1, right? All the possible outcomes, add up all the probabilities of each one individually happening. The probability should be 1, right? One of those things has to happen with 100% probability, right? Or percentage. And so here, the probability of the sample space must be 1. All right, I'll clarify here because we haven't really seen notation like this before, I think. Have we? We haven't seen anything like this with the probability. No. Trying to remember the rest of the course. The probability of the sample space must be 1, which is really saying one of the possible outcomes has to happen, right? Otherwise, you haven't listed the entire sample space. So one of the possible outcomes must happen is what that means. So if we go back to your formula sheet, the probability of A, which is the probability of anything, right? A is just a placeholder in this case, has to be between 0 and 1. Okay? Really just a reminder. But then the sum of the probabilities of all outcomes in S must be 1. Huh? We're usually just using this fact to check our work, right? Make sure that all our probabilities add to 1, otherwise we forgot something, right? We'll also use it in the complement property, but I'm holding off. I am, even though oh, you know what? I think we're going to use those dice again. So I'll bring it down here. If 2 dice, one red and one green, so same scenario that we've seen, are rolled, find the probability that the red die shows a 3 and the green shows a 6. And so we need the red one to show a 3 and I'll kind of underline this, and the green shows a 6. Why did I underline the and? Right? There's only one such outcome, right? And that's here. What if it said or? Right? Then what outcomes would satisfy the red one being a 3 or the green one being a 6? Well, that's all of these outcomes, right, that I've highlighted. Right, and so the and is the overlap, right, versus the or, which we'll get to eventually, right, but I just want you to see it right away, is going to be all of these possible outcomes. Notice that we count this overlap twice then, right? And so we'd have to subtract it. But there, I just gave it away. I gave it all away. It's all we're building up to today, I think, but basically. So we want to find the probability. Find the probability that the red die shows a 3 and the green die shows a 6. Oops. Now I just made this up, right? You can write it out full in words, right? But if it's obvious, right, from the question and what you're about to do, then you're allowed to kind of invent some shorthand, right? So the red one being a 3 and the green one being a 6, fine, is, and I'll bump this over here. What you want to do, same as the probability of just rolling a 2, for example, right? What did you need to do? You had to take how many outcomes you're talking about and divide it by the total possible outcomes. Now here we have 6 by 6. And so we have 36 possible outcomes, and we are talking about one possible outcome. And so in general, the number of outcomes divided by the number in the sample space, or maybe I'll just use, actually, can I just introduce some new notation? N of S. Now, N of S, where N of S, N, a lowercase n is used to denote the sample size. And so in general, a lowercase n is used to denote the sample size. Is the sample size of S. Right, we just learned this. Okay, so if you have something on the outside and then brackets and something on the inside, you read it as of S, right? And so the sample size of S. And I'll make a note here. N is generally used to denote sample size. Oops. Which you've probably seen if you're reading news articles and things like that. It would say maybe something like n equals 50, right? Saying the sample size for this study was 50 people, for example. Right. So now I'm applying it in N of S, as in the sample size of S. Huh? This looks like one word. Space it out just a smidge. So in general, the probability of whatever it is you're interested in is going to be the number of outcomes that satisfy, right? Whatever is on the inside here divided by the size of your sample space. Oh. Nice. Any questions about that? So far, so good. Okay. If two dice, oh, sorry. An event is a subset of a sample space, right? And so it's some smaller group, right, of the sample space. So if an event consists of only one outcome, it's called a simple event. That's not something that I need you to worry about, right? I just need you to be able to find probabilities. Okay? And so this is just one outcome in the entire sample space. And so it's called a simple event. Whereas if two dice are rolled, find the probability that the sum of the faces of the dice is 7. Committing. Now I did a cheater version, or what I like to call a Martha Stewart version of our dice. Because that's just make work. We don't need to do that. Huh? So the sum, roll a 1 and a 1, the sum is 2, 2 and a 1, the sum is 3, and I think the rest is pretty self-explanatory. Huh? The size of my sample space is still 36, right? And so that's nice. And I want to find the probability that the sum is 7. So what I want to do is just go through and find all the sums that are 7. You'll notice a pattern. Cruise around, make sure you didn't miss any. Right? But now I have multiple outcomes that give me a sum of 7. So the probability of a sum of 7 is the number of outcomes that have a sum of 7, right? Which is 1, 2, 3, 4, 5, 6. So there's 6 of them divided by the sample size of my sample space, N of S, which is still 36. Now, of course, if you try it on your calculator, 6 over 36 is roughly 0.1667. It's repeating, but bless you. Why do I want to check this? I want to check it, bless you again, because it has to be between 0 and 1, right? And so you always want to make sure that whatever you're telling me is a probability, it has to be between 0 and 1, right? Which, with practice, you can see that this will be between 0 and 1, but it's easier to see with the decimal, right? So I like to do the conversion, but if you want to use just the fraction, totally fine. They're the same. I guess I rounded it, but still. I'll make a note that that's what we did. Bless you. Make sure the probability, I'll say the probability is between 0 and 1, which it is. For probability problems, we love to have a jar of marbles or something kind of like that, right? Pulling socks out of a sock drawer, that kind of thing, right? So here's our first one. A jar contains 3 red, 4 white, and 3 blue marbles. If a marble is chosen at random, what's the probability that the marble is a red marble or a blue marble? Now, what we need to know is, well, how many total marbles am I drawing from, right? And so the probability of a red or a blue, right? Again, context tells me what those abbreviations are, right? You can write them out in words if you want, but I think context makes it clear. Is going to be out of the total of 3 plus 4 plus 3. Make sure Katrina can come back in. There's 3 red marbles, 3 blue marbles, right? And so 3 plus 3 out of 3 plus 4 plus 3. And so that is how we find the probability, which I suspect even before talking about sample spaces and things like that, you could have answered this problem already, right? Just kind of a little bit of problem solving, right? But 6 out of 10. Oh, nice. And that's it. That's the answer. Oh. You can make sure it's between 0 and 1, but it will be, so that's good. What if a jar contains 3 marbles numbered 1, 2, and 3? Right, and so kind of bingo style, right? 1, 2, 3. And if 2 marbles are drawn without replacement, which is exactly as it sounds, right? So you draw a marble, now it is gone, right? And you can't pull it out anymore. What is the probability that the sum of the numbers is 5? And so just as a little side note, right, the 2 marbles in this example are drawn consecutively without replacement. So you draw your first marble and then your second one. Yeah. Yes. Rambling. So they're drawn without replacement. And so just to clarify, it's not replaced in the jar, which means that you can't pull it out on the second draw. We will look at the scenario where we do it with replacement as well, so that we can see the differences. Okay. We want to know what's the probability that the sum of the numbers is 5, which means, okay, I need to look at my sample space. I think the easiest way to list the possible outcomes, again, whenever you have kind of one thing happening and then another thing happening, or you can kind of imagine that, then a tree diagram is a really nice tool to have. And so you draw your first marble. And for the first marble, you have marble number 1. You have 3 choices. It could give you a 1, it could give you a 2, or it could give you a 3. And we're drawing 2 marbles total without replacement, which means that if I drew a 1, now what's left in the jar is 2 or 3. Oops, that doesn't look like a 3. If you drew a 2, what's left in the jar is a 1 or a 3. Right? And so you need to make adjustments depending on what you drew for your first marble, for marble number 2. And if you drew a 3, then you have a 1 or a 2 left. Now your sample space, we want to talk about the sum of the numbers. Right? And so at the end of each of these branches, I'm going to put the sum. And so here, S is going to be the sum, which is 3, 4, 3, 5, 4, and 5. So my sample space is really just 3, 4, 5, right? Those are my possible outcomes. And so here, S is 3, 4, 5. But they can happen multiple times. And so the size of my sample space is 1, 2, 3, 4, 5, 6. Right? 6 possible outcomes. And we want to find the probability that the sum of the numbers, sum of 5, is 5. Now, I see a 5 here and I see a 5 here, which means I have 2 out of the 6 possible outcomes. And that is my probability. Wait. Store. To be so quiet, and also I'm gonna sneak and see if they're not. What are you gonna do? They're not. Those scoundrels. Give a little talking to. He's like, well, I'm pretty sure you weren't here one of the days too. Fair enough. Fair enough. There. Probability. Done. That's why I closed it. It was done. Any questions about that one? Kind of fun. We have the same jar again. So a jar contains 3 marbles numbered 1, 2, 3. And if 2 marbles are drawn without replacement again, all right? And so when you're reading these questions, I do have a note for the assignment questions. I think it's for this section, but let me see. Where is it? I don't want to say. Okay, I didn't make the note until the 8.3.1 assignment, but unless the question says to sample with replacement, then you're allowed to assume that you're sampling without replacement, so you're not putting them back. It just makes it a little bit more fun / easier. Okay. And so if you're ever unsure, you can ask me, but you can just go ahead and assume that it's without replacement and that it has to say with replacement if that's the case. So Here it says without replacement, which is what we had before, and we want to find what is the probability that the sum of the numbers is at least 4. Now, this is one of those my pet peeves of probability questions. At least 4, I'm going to clarify, includes 4. And so 4 or above, including 4. If it didn't want you to include 4, it would say greater than 4. And that would be 5. Okay, so at least 4 includes 4. On the final exam, because that's our first test scenario of this stuff, I'll be really clear about whether it includes 4 or not, right? And if you're unsure, right, when you're writing the test, then just ask.
You will be there in exams.
I will be there, of course. Us and 2 other classes in the same, we're in S104. I know. It's the worst room. But I'm pretty sure we're the biggest class, so we get to take up the most space. So I'm gonna try to make sure that you get 2 tables. Have you guys been in S104? Right? It's the seats are comfy, but squeaky. And you get these tiny tables that kind of fold up. But I'll make sure that you get, or I'm gonna try to make sure that you get 2 each. So lots of room. Sometimes we can't make that happen. It's cozy though, because the seats are comfy. All right. And I was gonna say that's a long time from now, but it's actually kind of not. Yeah, can do it. I don't know about you guys, but I'm counting down the late classes. We only have 3 left after this. That's pretty good. It's easy. Okay.
I was silly and made math this time next semester too.
That is silly. That is silly. Math is a morning subject. I don't know why they put us at this time. Should learn it in the morning. Okay. What was I doing? At least 4. That's what I was doing. I was gonna paste this in here. So I am cheating and I'm just copying and pasting, but at least 4. Now it can be 4, 5, and that's it. Oh. Nice. So just as on this test that you just wrote, where I got you to make a Venn diagram, right? And then you answered questions using the Venn diagram, right? Kind of similar. I make you create one tree and then you can answer multiple questions with that one tree, right? And so same idea. Okay, good. So then the probability, I'll put it over here, of at least 4 is going to be 1, 2, 3, 4 out of the 6 possible outcomes. Okay. And if you prefer to work with decimals, that's fine too. Okay. But I'll use the fractions because they're a little bit cleaner and exact. Nice. Any questions about that one? So now we're doing the same thing, but with replacement. So we've got the same marbles, 1, 2, 3. If 2 marbles are drawn with replacement, right? So if you've drawn it, then it goes back in and you can draw it again. Then what's the probability that the sum of the numbers is 5? Now we're going to solve it the same way, but our tree has to reflect the with replacement, right? And so, oops, give myself a little bit more room here. So I've got my marble number 1. 1, 2, 3. I should have given myself more room. Sorry, I'll try again. 1. That's not more. There. I need more room because for my second marble, each of these will have 3, right? Because they go back in and I have 3 again, right? And so for marble number 2, I have 1, 2, 3, 1, 2, 3, 1, 2, 3. And that's because of the replacement. Hey. Some of these were so long. There. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2. Oops, that just looked like a 2. 3. Again, we want to know the sum. So now I have the sum of 2, 3, 4, 3, 4, 5, 4, 5, 6.
I thought there was 3 marbles.
There are 3 marbles, but we're only drawing 2. Yeah, you want to keep those separated. And we want to know the probability that the sum is 5. And so same deal, we're going to go through and just highlight which ones give me a sum of 5. It can be drawing a 2 and then a 3, or drawing a 3 and then a 2, and that's it. So the probability that the sum is 5 is there are 2 of them. I have to change the number of outcomes, right? Because I'm drawing with replacement, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9. What's really nice, and kind of a nice way of tying back into what we found before with our slots, right? Is if I asked you, hey, how many ways could I draw 2 marbles from 3, right, with replacement? So then in terms of your slots, right, you would have your first marble, you have 3 options, and then your second marble, you have 3 options again, which is how you get 9, which is the same 9 as we have down here. So if you don't feel like drawing a tree, although the tree is nice to visualize the outcomes, right? But you know the total possibilities is 9. Nice. Oh yeah, that's what I wanted to say. So the probability that the sum is 5, now for comparison reasons, 2 divided by 9 is 0.222 repeating as a decimal, because I want to compare it just briefly to the sum of 5 without replacement, 2 over 6. So the probability of having a sum of 5, right, depends on if you're doing with replacement or without replacement, right? It's going to be higher if you do without replacement. So they will not be the same. By that logic, do you think that the sum is at least 4 will be the same? Probably not, because we just saw why. 666. But let's do it just in case. I've got this. Sorry, let me move this down. I feel like we're going to use it again. So I'll move it down here. Not for a while. So same jar, 2 marbles with replacement. What's the probability that the sum of the numbers is at least 4, which includes 4? Again. I'm going to steal this. And erase this. Good. So at least 4. 4, 4, 5, 4, 5, 6. Ah, 6 in the mix. So the probability of at least 4 is 1, 2, 3, 4, 5, 6 out of 9 possible outcomes. Which is the same. But they don't have to be the same. It just happens to be the same. Ah. If a 6-sided die is rolled once, find the probability that the result is greater than 4. Might be nice to list the sample space. The sample space, bump this up here, is a 1, a 2, a 3, a 4, or a 5, or a 6, right? For a 6-sided die. Roll it once, and we want to find the probability that it's greater than 4. And I will clarify here. It has to be greater than 4, not including 4. Or did I? Oh, yeah. At least 4, right? Includes 4. Greater than 4 does not include 4. But like I said, again, if you're confused about that in the exam, then just ask. Okay, but try to make it clear. Greater than 4, not including 4, well, that's a 5 or a 6, which are 2 out of the 6 possible outcomes. And so the probability of greater than 4 is 2 over 6. Nice. Questions? Curious to know. Okay. We're just blowing through these. I was worried I wouldn't have time, but I think. Okay. Still a lot left. But we will have lots of time. So that's good. Let me What's really nice about ending with this section is that there's a lot of overlap from logic and set theory. And so we'll have seen a lot of these things before. We changed the notation just slightly for probabilities, but the ideas all stay the same. Which is also nice because then you get to go back and practice the old stuff a little bit. All right. 8.2. I know. Can you believe it? 2 sections in one day, the nerve. It's crazy. But it means we'll be done new material so much faster. Which is nice. Mutually exclusive events and the addition rule. So in chapter 7, we found the union, right, which was this U, which is the or, right? The intersection, which is the upside down U, which is the and. And we found the complement of a set. And so if we have a set A, then we use the complement with a bar over it, which is everything in the universal set that's not in A. So I tend to read it as not A. Now we're going to use these set operations, is what they're called. And we're going to describe events. So the union of 2 events, E and F. So E and F are going to be generic placeholders for any events. Often we'll use A and B, but for some reason this textbook uses E and F, which is fine. So I'll just stick with that. So E or F, right? What's nice is you already know how to read this, right? E or F. Is the set of outcomes that are in E or in F or in both. Now that's the one that everyone forgets about, is that it's allowed to be in both. So if it's in E or F or in the overlap, that both of them are satisfied. The intersection of 2 events, E and F, is E intersection F, or how we usually read it is just E and F. And that's the set of outcomes that are in both E and F, right? They have to be in both. Introducing some slightly new notation, not a new idea, but new notation. The complement of an event, E, is denoted by E superscript C, the complement. And so here, this is new, new notation. Right, versus the complement of E, which was for sets, right? So for probabilities, we use this E superscript C, the complement of E. And it's a set of outcomes in the sample space that are not in E. One thing that's on your formula sheet is that the probability of the complement of E has to be 1 minus the probability of E, right? If I tell you, oh, the probability of someone getting an A in this course is 20%, then what's the probability that someone does not get an A? You know that that's 80, right? because, well, you either got an A or you didn't, and that's your sample space, right? And so you already intuitively know what these complements are and what the probabilities are, right? And so here's how you say that with notation. Right? The probability that the complement of E is going to be 1, which is technically the probability of the sample space, minus the probability of E. Right? And so this is from the fact that if the sample space has n elements and E has k elements, then the complement has n minus k elements, right? And blah, 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 blah. If you go to your formula sheet, let me put a little markup here to bump it up. The complement property is the next thing on our formula sheet, right? So we're just powering through these today. So the complement property, second time I wanted to say party. The probability of E is 1 minus the probability of the complement of E, or vice versa. Right? Swap back and forth, but it is on your formula sheet. Now, in the example, right, people get an A in this course or they don't, right? Those are all the possible outcomes. There's only 2 outcomes, right? But someone is placed in one of those 2 categories. There's no overlap, right? And so what we call that is mutually exclusive. Right? And so events whose outcomes do not overlap, we call these events mutually exclusive. You might have heard the term disjoint or disjoint outcomes. Oops, let me put that down here. But mutually exclusive is a term that people kind of throw around in regular speech as well. Oh, no, that can't happen because they're mutually exclusive, right? Which really just means they can't happen at the same time and no overlap. I'll clarify down here. I think maybe I'll do this. Copy. I'll make a note here. Mutually exclusive if the 2 outcomes can't happen at the same time. All right, just as a quick example, a student gets an A or doesn't. Right, and so the complement is always mutually exclusive of the original event. In terms of the sets and the possible outcomes, it means if they can't happen at the same time, right? There's no overlap, then E and F has to be the empty set. And so we use this fact quite a bit. If you have a Venn diagram, consider a Venn diagram, a generic E and a generic F. then this region here is E and F. Now, if they can never happen at the same time, right, then it would look like this. E, F. Mutually exclusive. Usually what happens is we still draw the overlap, but then put 0 in the overlap, right? But just to visualize it, because I do this a lot where I have mutually exclusive kind of two circles and I pull them apart to remind myself, okay, no overlap, right? And so here, mutually exclusive. Or usually we still draw the same Venn diagram, E, F, but with a 0, right? Or just kind of nothing in there, I guess, technically. Let's say there's 14 here and 17 here, and leave it empty or 0. Those would be the counts in each of the areas anyways. Oh. Nice. So if E and F is the empty set, then we say they are mutually exclusive. But really it comes down to, can they happen at the same time? Yes or no, right? If you roll one die, you only get one of those possible outcomes. And so each outcome, they're considered mutually exclusive. And uh-oh. Now I've done it, haven't I? Because I pasted, I'll redo this. Ooh, nice. Card, and we love these card problems. And I used to get nervous with card problems because I'm not very good at cards, right? I don't know a lot about cards, but if I have to use a card problem, I'll try to avoid it. But there are card problems in your assignments, and so I want to talk about a deck of cards, a standard deck of cards, just so you kind of know some key things about a deck of cards. But first, let me bring in my prop, if you will, here. And maybe I'll just bump this up here, actually. So it's from a different course, but you can just ignore a lot of this and that. But it was the only deck of cards that I had handy. Standard deck of cards. Card facts. There are 52 cards in total. There are 26 of each color, being black or red, clearly. There are what we call 4 suits. And the suits are clubs, which I can never remember because I want to call them clovers. Spades, which looks like a shovel, and so that kind of makes sense. And then hearts and diamonds. And so those are what we call the suits. There are 12 face cards. Of the face cards, there's the Jack, the Queen, and the King. I don't like to do card problems, but there are a lot of card problems that we could solve. And of course, it's interesting, right? Once you get into probabilities, right? Because if you know that 2 jacks are already out on the table, then that's sampling without replacement, right? That's going to affect the probability of a future jack, right? Now there are only 2 jacks left that you know of in this deck, right? And so you can adjust the probabilities. And so, like I said, there are a lot of interesting card problems that we can solve. And so it's worthwhile getting to know a deck of cards like this. But just the basics, nothing. I don't want you to know hands or anything like that, right? Full house and a flush and all those things. I don't know those things. So here we have this deck of cards, and a card is drawn from a standard deck. Determine whether the pair of events is mutually exclusive. And so E is defined as the event that the card drawn is an ace. And F is defined as the event that the card drawn is a heart. Now I'm going to snag just the cards. So we can look at them. So if I have E, let's circle all the events in E with this orange. The card drawn is an ace. Oh, and I think I forgot to point it out, but these are the aces, right? And they can be high or low, but it doesn't matter for us. So these are all in E, right? Which means I have 4 outcomes in E. F, the card drawn is a heart. Okay. I'll do pink for hearts, or I should do red for hearts, which gives me all of these cards. Now, there is overlap here, visible overlap. That's what's nice about being able to visualize your sample space, is you can actually see the overlap, right? So here, this is the troublemaker. And maybe I'll do this. Copy. Gotta make room. Need a lot of room. We used red for F. E and F is the ace of hearts. Oops. which is not the empty set, right? There is one card in there, which is not the empty set. Therefore, E and F are not mutually exclusive, right? It is possible to draw a card and it be in both of those sets. And it's the ace of hearts. Nice. Good. Any questions about that one? Back to our dice. 2 dice are rolled. Determine whether the pair of events given below is mutually exclusive. The sum of the faces is 6 and 1 die shows a 4. Now, I will bring in the entire sample space so that we can look at it, right? But if you can just think of one scenario where there's overlap, right? Then they're not mutually exclusive, right? Even if there are more, right? You only have to come up with one counter example and say no, because this can happen. And so here, we only need to think of one example where both G and H are true to conclude they are not mutually exclusive. Right? If it's possible that they can both be true, then they're not mutually exclusive. To prove they are not mutually exclusive. No. G, the sum of the faces is 6. And H, 1 die shows a 4. So in my example, consider I roll first a 4 and then a 2, then the sum is 6, right? Which means that G is satisfied and H is satisfied because there's 1 4. I will clarify that this is going to mean only 1 4. It shows a 4, only 1 4. I can think of another example, 2 4. Right? Would also give me 6. But let's have a look. Again, pre-baked copy with all the sums. Hey. In green, I'm going to highlight everything that's in G. The sum of the faces is 6. That's here, 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 here. And I'll do, let's see if I can find a non-yellow color. How about orange? Orangey glad. H, 1 die shows a 4. If 1 die shows a 4, then the red one can be a 4, or the green one can be a 4, but not both at the same time. Okay? Which means not this one here. And so can be these, or these, or these. Now it's kind of hard to see, so I'll circle them as well, but these, just as I expected, are the ones where, oh nice, where both of those events are satisfied. All right. So G and H is the set of 4, 2 and 2, 4, which is not the empty set, which means they are not mutually exclusive. And notice I skipped 4, 4 because that would not be an H, right? Because only one die shows a 4. Huh? The family has 3 children. Determine whether the following pair of events are mutually exclusive. So can they happen at the same time? So what we need to do is we need to list all the possible combinations. And I assume we're talking about gender here. The family has at least one boy and the family has all girls. And so assume only boy, girl possible. Three kids, whoa, all right. It's a big tree. Child number 1 is a boy or a girl. Then child number 2, boy, girl, boy, girl. Third one. Oof. But this is similar to what you did. I think it was on the practice test, right? You flip a coin 3 times. What are the possible outcomes? It's the exact same question, right? It's just instead of heads and tails, it's boys and girls. Boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy. I should have had this pre-baked. Girl, boy, girl, 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 boy, girl, girl, girl. M, I'll use orange. The family has at least one boy. Okay? At least one means one or more. Okay? And so that's true here. This is 3 boys, this is 2 boys, this is 2 boys, but in a different way. Here's 1 boy, 2 boys, 1 boy, 1 boy. Only one that's not in M is all 3 girls. Now, that looks like it's going to be in N. The family has all girls. Hmm. Since M and N equals the empty set, they are mutually exclusive. Another thing to note, and a trick that I'll like to use, especially later on in probability, and I know we only have days left, but so it's not that far off, but not today, but is girl, girl, girl is the complement of at least one boy, right? So if I want to find the probability of at least one boy, right, then I would have to add up all these probabilities, right? Or what I could do is I could take 1 minus the probability of all girls, and that should give me this probability, right? So it's kind of a sneaky way of solving problems is using the complement. So here, also notice N is the complement of M. And M is the complement of N. If a die is rolled, what's the probability of obtaining an even number or a number greater than 4, not including 4? Okay. So now, my sample space, I roll one die, I have 1, 2, 3, 4, 5, 6. Unless it specifies, we assume it's a 6-sided die. I want an even number. So that's 2, oops, let's use yellow. 2, 4, or 6. Or a number greater than 4, or both, right? Or includes both. And so here, greater than 4, that might be a little dark, but 5 and 6. So if I count the number of highlighted outcomes, I want to find the probability of it being greater than 4. Oh, sorry. Probability of even or greater than 4. Forgot. I was thinking, haven't we done this already when I just said greater than 4? We have, but now we're doing even or greater than 4. Let me add page here. The number of highlighted outcomes is 4 out of 6. Whereas probability of an even number is 2, 4, or 6, which is 3 out of 6. And the probability of greater than 4 is 5 or 6, which is 2 out of 6. So, or or means addition, right? And means multiplication. And so when you first start tackling these problems, you might say, okay, well, the probability of it being even is 3 and 6, and the probability of it being greater than 4 is 2 and 6. But what that doesn't take into account is the overlap, right? The fact that 6, the outcome 6 is in both of these events, right? And so we need to subtract the overlap, right? Because 3 plus 2 makes 5 over 6, but we know it should be 4 over 6. And so that's where we need to have this rule, this addition rule. It's called the general addition rule. The probability of E or F is going to be the probability of E plus the probability of F minus the overlap. And so here, minus the overlap. Oops. And this is the probability of E or F. And this is the probability of E and F. As a special case, so if and only if E and F are mutually exclusive, meaning there is no overlap, then the set itself, E and F, is the empty set. But if there's no possible outcomes, the probability of that set is going to be 0, right? Which means that this, you would just be subtracting 0, right? Because there's no overlap. So we don't need that special case, because if you always just use the proper formula, then you go ahead and you find that, hey, the probability of those two things happening at the same time is 0, then you could just sub 0 in there. So we don't need this special case, but which is why it's not on your formula sheet. You just have the addition rule. The probability of E or F is the probability of E plus the probability of F minus the probability of E and F. The trick is, if I give you 3 out of any of those 4 components, you can solve for the 4th one, right? Now, that sounds reasonable, right? But reading questions and figuring out, okay, what probabilities do I have, right? That's going to take some practice. So let's practice. So if a card is drawn from a deck, use the addition rule to find the probability of obtaining an ace or a heart. So we want to find the probability of an ace or a heart. And maybe, for simplicity, instead, I'll define ace as A and H for heart. So then what I want to find is A or H, which is the probability of A or H, like this. I'm just going to highlight it, but I will. So that's what we want to find. Now the probability of A or H, what you want to do is map it back to, okay, this is the general form on your formula sheet, and maybe I'll snag the actual formula sheet one. Copy. And this is where it gets just slightly confusing, at least when you're starting out, I think, is you want to map this generic E That's just a placeholder. So wherever you see an E, you're going to write A. And wherever you see an F in the general formula, you're going to write H. And so the probability of A or H is the probability of A plus the probability of H minus the probability of A and H. So replace E with A and replace F with H. Now it's on your formula sheet, so you don't have to memorize it, but it'll always be the first one plus the second one minus the overlap, right? Both of them together. So this means we need to find the probability of an ace. Now I know that there are 52 cards in a deck, and we've already seen the deck of cards, and we've already seen that there are 4 aces. So the probability of an ace is 4 divided by 52. The probability of a heart, P of H. Right? Now notice these standalone probabilities, they don't care about the overlap. We deal with the overlap later. Right? And so it's just how many hearts do you have? Right? And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, because there are 13 of each suit. So 13 over 52. And we've already seen the overlap. There's only one overlap, right? But that still counts. We have to subtract it because the ace of hearts is in this 4 as well as this 13, right? And I only want it in there once. I do want it in there once. And so I have to just subtract the 1 overlap of over 52. Now I encourage you to use your calculator, or what's nice is if you keep all of these as the same denominator, then you can just add and subtract with the common denominator. And so this is going to be the same as 4 plus 13 minus 1, all divided by 52. Which puts me at 6 over 52, which as a decimal is roughly 0.1153846,154. Which, oh,
How do they give you 6 over 52? Isn't it 16? 4 plus 13 is 17 minus 1 is 16.
well, if you don't punch it in right, you get a very special number. Thank you.
I was like, did I do the math wrong? I'm pretty sure it's 1 6.
Let's try again. I feel like you caught it in time. I don't have to do the punishing red. 3.076923077. Or roughly 30.8%, which is usually how we communicate probabilities, right? When we're just talking, okay? Or writing reports. But probabilities have to be between 0 and 1. Okay. Nice. How am I doing for just like that, huh? Well, I'll leave these. Can't believe we ran out of time. We'll do these for review next day. because I am out of time. I am. Time flies when you're having fun. If you have any questions, let me know. Otherwise, I will see you on Wednesday.